Why is it? Highly attended, yes. Ooh, this one is shiny. Now I have to use this one. Nope. It's the same. Black. And a new glove. It's not going to do it. Just some background music. Oh. It's not a bad idea. Now I can just generate it. That's over here. For now, I can just generate it forward. Highly unattended. Is that pretty, right? Trigger number, please. Trigger number, trigger number. All right. Hold on. Bad things are happening. All right, welcome. Let me just know, can you verify that you can hear me? Should double check if my sound settings are correct. Okay, good, good. Just paranoid, just want to be sure. All right, so we are today going to talk about our next chapter, which in the newest problem book is on related rates, chapter 11. Sorry, we're going to talk about related rates, which is numbered in the newest version, chapter 11. Now this is still the end of the previous group, even though it's not going to be in midterm 3. It still has got to do with mainly derivatives before our next chapter, which is going to be a little different. So let's just see, how do we want to see the derivative? What have we done up to this point? Let me just shift. What have we done up to this point? And how can we see derivatives in a different way? So so far we have, let's say we are given a function, and let's suppose it is f of x, and we don't have to make it too complicated. Let's say x cubed plus 4x. Then we are used to finding the derivative. Whoops, that was ugly. I did swap out my drawing pad. Derivative, but apparently I can't spell now. Derivative, yeah. We find the derivative. We call it f prime when we don't need to be too fancy. And basic properties for this function gives us our derivative. Now, of course, more complicated function, different properties, but still, this is how we do it. Alternatively, we can do the same thing, but instead of seeing the function information, I want to see it as an equation. There's no difference here. It's not even a different view, it's just another view of doing the same thing. So we can instead say, given an equation that determines how y relates to x, we can write the exact same thing we did before, but with more of an equation look to it. It didn't change the information in any way, but it's just an alternative way to look at the exact same thing. Then when I want to find the derivative, of course the derivative is going to be the same, but looking at this as an equation instead of a function, I can now say, well, I have a left-hand side of the equation, which is equal to the right-hand side of the equation. So we'll just write it that way for short. Then if these two sides, their things, there is the same because of the equal sign. Equal means exactly the same. If they're the same, that means their derivatives have to be the same as well. So I'll write it like this. The derivative of the left-hand side has to equal the derivative of the right-hand side. Now this is complete overkill in the most basic situations, but it allows us to do fancier things, which we'll see in a second. So if I see it as an equation, I have two sides that equal each other, two things. The right side rather, has a lot of detail. It shows me exactly what is happening to x to get the result. The left side is a little bit more cryptic. It is just represented with a y. But because these two sides are the same, everything is going to be the same, whether I see the detail or not. So their derivatives, their tangent lines, everything will be the same. So if I now plug in their detail, the left-hand side was just y, and the right-hand side was x cubed plus 4x. Then the left-hand side, I don't have any information. If I just look at the left, I don't see anything else. I don't have any information to know what y actually is, so I can leave it like this, but the shorter version is dy dx. Any of these versions, big D notation, little d notation, they're all the same, of course. So all I can say is, well, the left-hand side is the derivative of y. I don't know what else to say, so I'll leave it like that. But on the right-hand side, I do see the detail. So I know exactly what the derivative is going to be, and I can simplify that according to our familiar derivative properties. And of course, we're doing essentially the same thing, and our answer has to, of course, be the same. But it's all a matter of how do I view the information? Do I see it as a function? Well, with that comes some limitations that it has to be a function. I have to have an input, x, and when I do a calculation, I get a single y value. The right-hand side is a little bit more general. It overlaps in the case that I have a function, but when I see it as an equation, it allows me to do more things. Because, I'll write it like this, there are more things, and I use things in the most technical way, than just functions. Things that have graphs. For example, the simplest one that you may be aware of is the equation x squared plus y squared equals, let's go with 1. This is not a function. Not a function. The most simplest way for us to notice that is that I can't solve, that's an ugly E, oh. I can't solve for y uniquely. Yeah, maybe in school you wrote y equals plus or minus square root of 1 minus x squared, but it's not unique. It has a plus or a minus, which means that if I was given an x value, for example, if x is equal to, let's go with, I don't know what, What should we go with? Maybe 0.5. Sorry, it's just going to pop up here. If x is equal to 0.5, for example, then y is equal to positive root 1 minus 0.5 squared, but also y could be negative root 1 minus 0.5 squared. They would both be, work in my original equation. So what I get as a graph is, in this case, a circle. Try and center this thing. I get a circle with radius 1 centered at the origin. So when I have like a 0.5 x value, there are 2 points that satisfy the equation. And this is not a function anymore. Yet, I do have a graph. I do therefore have the question of, well, if I look at this point, what is the tangent line at that point? I still have a tangent line. That means I still have rates of change and all those things, even though I don't have a function. So we still have the derivative question, the derivative issue, even if we don't have a function anymore. And the way of looking at derivatives that we originally did is kind of limited to just functions, which is fine for the most of the time, but not always. If I switch my view to this equation view, then I'm able to handle these more general things, these more general situations. They're not called functions anymore. They're called just relations, which is the bigger group that contain functions. They have graphs, but I can't solve for y and get a unique output for every input. Not a big deal for us, except in this chapter, kind of. So we can have a circle. Let's stick to the circle and see, well, if I want to ask the question, let's make a question. Let me erase this nonsense here. Oh, my eraser is super small. Get out of here. Okay. So if we have a question, I know that x squared plus y squared equals 1 has a graph. The x values, so let's say this equation, rather than calling it a function, it's not a function, is defined, let's not say on, for x going from -1 to 1. That means that there are points for all these x values, points on the graph, like at 0.5, for example. So we could then ask, what is the slope of the tangent line at x equal to 0.5? There's a graph. There's a point on the graph. It's up here. Now, there are other requirements, but there's a tangent line, so the slope question, which means the derivative question, is still a valid one. But I'm going to have to see this with the right side view if we're going to find the derivative, because I'm not able to write y equals something. All right. Luckily, it is quite simple. I write my equation, and I don't bother to solve for y. Even if I feel like I could, this plus minus root version is not something I want to work with. So I just leave it in its nicest form. No roots, no plus minus options, nothing. Nice and simple equation. It's really not a bad equation. All I have to remember that there's a left-hand side, and there's a right-hand side. And they're equal, meaning their derivatives will be equal as well. Whatever they are, whenever we do this, this is called implicit differentiation. Differentiation is the process of finding a derivative. Differentiation. Implicit. So I'm not able to solve for y, like up here, whoopsie, up here, here, if I write y over here, whenever I'm able to solve for y, we could say y is explicitly defined by this function. Whenever I have a function, y, the function is explicitly defined. It's telling me exactly what the calculation is to find the output value. When I have something like a circle, there is still a relationship between y and x, giving me all the points on the circle, but now y is implicitly defined by this equation. I can't solve for y. We then say it's implicitly defined. It is defined, but I can't quite see what the calculation is looking at this equation only. So when we try and find the derivative of an equation that is not solved y equals something in x, implicitly defining the relationship between x and y by taking the derivative of the left-hand side equals the derivative of the right-hand side, we call it implicit differentiation. Now, I'm going to do the right-hand side first, because it's super easy. Derivative of a constant is 0. Not much to do. And often for these guys, for our equations anyway, one of the sides will be super simple. Not always, but often. So now, what property do I use for the left-hand side first? Well, I see I have multiple terms, so it's going to be the sum property first. So I'm going to do some detail here, which of course you don't have to do every time. But just to show, my properties are still there. They're not going away. I use the sum property just like I always do. Now I have two of these things to resolve. Sorry, this looks bad. The derivative of x squared is 2x. Power rule, nothing has changed. However, something is different in this the second term derivative that we need to figure out. Because let's just pretend we don't exactly know the graph. We don't know if we can solve for y. Maybe we can. We don't really care. This equation originally looks so nice. We're just going to work with that. And just for the sake of simplicity, I'll call y a function. Y is some sort of function in x. I just can't see the detail. In this first term derivative here, I see the detail, so I'm able to use my properties. I can't use my properties as easily if I can't see the x detail. Can't see the detail. Can't see the x detail, we'll say. So I can't use the power rule directly. I can't use the things that I'm used to. But what this is going to require is when I realize I have a function, and then I square that function. This is a function of a function. So this requires the chain rule. Even though I can't see the inside function's detail, I know it's there, and I am doing something to that function. So my inside function is y, my outside function is y squared. The chain rule says take the derivative of the outside function, 2y, times the derivative of the inside function. But now with this approach, I can't see the detail of the inside function to do that second part of the chain rule. So all I can say is, look, I know I have to do it. I don't know what it is. I'm going to stop there and just leave it in its named form because I don't know how to go further with that. But that's also not the goal. The goal is to find this. So it makes total sense that I don't know it. This is what we're looking for. So it totally makes sense that I don't know what it is. I'm trying to find it. So then all I need to do is isolate this dy dx because that's the one I'm looking for. So let me not skip any detail. I move the 2x to the other side, and then I divide both sides by 2y to get negative x over y. So this tells me that whatever the point on the graph is, I need to find the x value and the corresponding y value to determine the derivative. The derivative now doesn't just depend on the x values like we've seen before, it now depends on both coordinates of the point for these more interesting graphs and equations. So if I now, I'm going to squeeze it in here, if I now want to say what is happening at x equal to 0.5, for example, then I need to know what is y. Now let's suppose we are only interested in the top one. So let's just say here y positive, because looking at the graph, I'm going to get two of them, right? I have a plus and a minus up here. So I'm going to focus on the plus one, just so we have a single point. So it's the positive root of 1 minus 0.5 squared. Positive root 1 minus 0.5 squared. And I get that not by solving for y, but by plugging it into my original equation up here. So let's perhaps do that. Let's do that. Let's do that instead. Oh, I can't backspace. I can't undo. I'm going to have to erase this guy. Just to emphasize what we're really doing, I'm going to put it in. Let's erase that as well. I'm going to put it into my equation. So 0.5 squared plus y squared equals 1. And then find the y value. So y squared equals 1 minus 0.5 squared. Get out your calculator. It's always nice, even though you're not here in person, to do it with me. This calculator scares me with all its right-hand side buttons. I need to practice this thing more. 1 minus 0.5 squared. That looks good. So I get 0.75. And then I'm looking for the positive root of 0.75. We'll just stick to 2 decimal places in case we have to. Where's my calculator? There we go. 0.75. So do I do the square root first? 0.75. It's very important to be familiar with how your calculator works. 0.8. Oh, because I have a 0 there, I'm just going to go 0.866. It's so nice. So right here, 0.866. So the point in question I now know, when x is 0.5, y is 0.866-ish. And I need both of them to be able to find the derivative, which is the slope of the tangent line. So we're going to write it like this. So let's say it in words first. Slope of tangent line at the point with coordinates 0.5 and 0.866 is the derivative. Still has this, oops, that was supposed to be an x. Still has the same name. Is my camera not working anymore? Oh, my camera's not working. I have a frozen polar bear. Anyway, let's just finish this before I look at that. I'm going to write a line and then the point in question. Now, it's okay if you are not super strict with the notation, I understand. Regardless, I plug them in. 0.5 for x, 0.866. Now, I know you need to pick the original, but I'm still going to write a rounded version. Let's go back to my calculator here. Can I memory this guy? How do I? Oh, no. I want to put that into memory. No, that doesn't work. I want to. Okay, I can't. Let's not worry about that. 0.866 is fine. So 0.5 divided by 0.866-ish. So of course I can't look at the decimals too far, but I'm going to get negative 0.5. And I just saw it. What is it? Let's say 77. Now it totally makes sense that it's negative, because my positioning of the point in the graph does suggest that I'm going to have a negative slope. How steep it is, who knows? Who knows? We now found a way. Let me zoom out a touch. We now found a way to calculate what the slope is, even if I do not have a function. Let me pause to see if there are any questions while I'm trying to figure out what is happening to Mr. Polar Bear. No, bring back the polar bear. Why? Totally frozen. I'm just trying to restart it. Are there any questions at this time? Polar bear might be frozen forever. Let's see if he can come back. Just had to restart him. So implicit differentiation doesn't have to be complicated, especially at our level. Let's see if we can bring back the polar bear, because I want to. Doesn't seem to. Oh, am I back? Maybe. Anyway, it's all good. Let us do one more example, if there aren't any questions. Just hold on 1 second. There's just trying to reply to a text. In Discord. She is in the wrong chat room. This one. There you go. I have moved you into the right chat room. The open chat is just for people who want to chat with each other, or say, hey, let's get together in a private room or something. Whenever there's a lecture, we're in a classroom. All right, so we've done one. Let's do one that is a little bit more complicated. Though the basic method is the same, I'm just not going to always be able to know what the graph is. Let's make a new page here. Zoom, zoom. No, that's not zoom. This is zoom. All right. Let us see. Let's get some problem book questions here. Ooh, let's pick something interesting. Well, I don't know the graphs of any of these, so let's not make it too bad. Let's take this one. This 3y cubed. Minus 8y squared. No, was that right? 3x cubed. That would make more sense. I should have x's and y's in there somewhere. Minus 8y squared equals 10y. All right. Not too complicated, but regardless of the complexity of the equation, I am going to do the same implicit differentiation strategy. Just triple check here. Doesn't really matter. Okay, so our goal is to check the question. Just find the derivative. If I want to plug in a specific point, then I can do that at the end, but the question just asks for the derivative in general. So I want to find dy dx. In an equation that is not defining a function, y is implicitly defined, I take the derivative on both sides, essentially, because the equal sign says left-hand side is equal to right-hand side, then the derivatives are the same. Their tangent lines are the same. Everything is the same in terms of rates of change. So now I look at what I have. Let's do the right side first again. It's the simpler side. I have 10 times y. Constant times a function property says it's 10 times the derivative of y, and I'm trying to find that, so I'm not going to know that right now. So I write dy dx. The right side, I'm going to use the difference property. I'm going to write it out in detail so that you see our properties aren't completely abandoned here. Difference property. Then the first one here has derivative 9x squared. Now the next one. Let me just respond in Discord chat here. The next one, I see that I have a y, which is, very loosely speaking, a function of x, at least on some portion. So it's a function of a function situation, which means I'm using the chain rule. The derivative of the outside function is with respect to this y, which is 16y, times, says the chain rule, the derivative of the inside function, which is exactly what I'm looking for. So this is always going to happen. Let me just finish my equation before I continue. This is always going to happen. If your variable, and this is why I love the big D notation, if your variable, x in this case, is the same as what you see in the square brackets, then everything is the same as always. There's no issue. But you see in the second one, my variable is not the same. That means I have a chain rule situation, which means that this letter inside the bracket is a quote-unquote function of a function, x, function of x. And what I have in the bracket is a function of a function, which means I have to use the chain rule. So if the letters aren't the same, then the chain rule is always what you're going to use. So that's really the only catch here. It's the only thing you have to watch out for, and then using the chain rule carefully. So now I have the situation. The derivatives are finished. I am only looking to solve for dy dx, and I'll be done. So you can do this one of two ways. I don't like negatives, so I like to move it to get rid of the negative, and then I'll swap everything around. So I'll move the 16y dy dx to the right, and then flip it over. But I cannot connect my d's. Then dy dx plus 16y dy dx equals 9x squared. So I moved the second term over, becoming a plus, and then I flip the sides to have my unknown dy dx on the left still. Then I am going to take out dy dx as a common factor and have left 10 plus 16y. The right-hand side is done. And then I'm going to divide by this bracket to get dy dx equal 9x squared over 10 plus 16y. So you see again that the derivative, which is the slope of a tangent line wherever I want it, depends on both x and y. Depends on both coordinates, the full coordinates of the point. I can plug in a specific x value and see what would happen. Let's try and visualize what's happening here. Whoops. Let's go back to my function here. I have a tool to graph these more complicated ones for me as well. The Desmos graphing calculator. Now I have to remember, 3x cubed. So I'll type in 3x cubed. No, how do you do that? That way, cubed. That is very strange. Why do you do that? Okay, so that works. I think I was pressing something at the same time. There we go. Minus 8y squared. 8, I think it needs the times. Y squared equals 10 times y. And there you see a very different graph than what we are used to. And I see that if I take, for example, x equal to 1 as input value, I have two y values. One seemingly around 0.25, and the other one looks like negative 1.5. But there is a graph, there are slope lines and everything. And therefore the derivative question is a perfectly valid and important one. But the way to find that is, because I don't have a function anymore, I use what we call implicit differentiation, which is this step over here. Implicit differentiation by taking the derivative of each side of the equation and setting that equal to each other. Are there any questions at this time? Have a look at the rest of the problem book. We will continue this. So you can do 11.1. 11.2, just give, you can ignore 11.2. I think it's fancier than a midterm question would be. I just want some variety to understand what implicit differentiation is doing. And it's doing something very simple, but something very powerful in terms of covering many more graphs than just functions. And then we will look at how implicit differentiation is used with some practical problems starting tomorrow. Remember that the midterm 3 is on Monday. If you have any questions about how that is going to go or how it works, read the announcements on Discord or send me an email or a message or whatever, but you have to be ready on Monday. All right, that is it for me for now.